Today, together with my colleague Andra Radu, we will talk about SystemVerilog assertions verification with SVAUnit in the first part of this two-part tutorial called SVA Advanced Topics, SVAUnit and Assertions for Formal. So before we begin, I would like to go through the tutorial's agenda. It will start with an introduction on SystemVerilog assertions, what they are, the main types available, what they can be used for, as well as their benefits. The next parts of the tutorial will focus on the assertion development flow, which will span from planning through implementation, and it will focus on verification. Verification will focus on using the SVAUnit framework as a platform for verifying your SystemVerilog assertions. We will then conclude with a set of common test patterns that we used for simple temporal expressions that you could find in the most common assertions. So without further ado, we can start SystemVerilog assertions. Now, I think everybody is accustomed to assertions, but a quick introductory. Simply put, an assertion is a check against the specification of a design that it should never violate. It verifies the properties of a design or of a protocol or an interface, properties that can be requirements from the specification, properties that can be defined either directly in an assertion, inline, or properties that could be defined separately as using the property construct from the SystemVerilog language. This allows you to do much more reuse, as you can use the property in several assertions. There are several types of an assertion could look like this. It is deducted from the specification of a design, let's say. One simple example would be this one. We have this requirement for this very simple interface with only two signals, request and acknowledge. The requirement is that the acknowledge signal should be raised no later than 3 clock cycles after the assertion of the request signal. Now, this property of this protocol could be translated easily into a property construction for the assertions like this one. But the property itself doesn't check anything. It needs an attached assertion to do that, like this one would be a simple one, in which we assert that this property should hold, otherwise we issue an error message. Now, this is how a simple SVA looks like. There are several types of assertions available. Immediate assertions that only check the condition of an expression at one moment in time. It doesn't span over multiple clock cycles. It just checks that the expression is correct or not. It is evaluated as an expression inside an if-else statement. And then you have concurrent assertions that check the value of an expression over multiple clock cycles. So, for example, we have the previous simple assertion in which we want the acknowledge signal to be asserted no later than 3 clock cycles. So, in the first 3 clock cycles of evaluation after the request signal arises, the assertion should pass. And if it is the acknowledge signal is asserted later than 3 clock cycles, it should fail. You may ask, there are several types of assertion languages available. Why use SystemVerilog assertions? Well, one thing will be that they're fast, so you can anchor them directly to the object under test without the use of any intermediary logic. Like, you don't need a monitor, you could just attach an assertion to the signals of an interface. We discussed there are two types of SystemVerilog assertions, immediate ones and concurrent ones. Now, where are assertions used? They can be used inside the verification component. That can be, let's say, an assertion package inside the verification component, which could be a block environment, which tests the functionality of a design, or it could be inside the universal verification component that tests the functionality of a protocol or an interface. They can also be used inside the assertion package that is used in a formal proof kit, which means that the assertions will not be exercised using a simulator, it will be exercised using a formal engine. In some cases, it is possible to use the same assertion package in both the verification component and also exercise it in the formal engine. More exotic cases of using assertions, it would be, in this presentation I saw it would be for RTL generation, in which they use prototype tool to generate synthesizable RTL prototypes using the assertions as a formal specification for the design. Also, another exotic use would be to construct test patterns automatically using assertions as the base of the design. And you may ask, why use SystemVerilog assertions? Well, as I said previously, they're fast, so you don't need any intermediary logic. You can just attach them to the interface, like in SystemVerilog, and check the signals. They're non-intrusive, meaning that you don't have to contaminate your design logic. You can have clear separation between the assertions and the definition code of the design. They're flexible, meaning that you could use them in both formal and in simulation. And one important aspect for verification, they're coverable, meaning that you can know how much you have checked and exercised using your assertions. And another fact it would be that they're built-in constructs. They use built-in constructs of the SystemVerilog language, so it's much easier for a SystemVerilog user to adopt them. The first step that you want to do in creating robust SVAs is planning them. Planning starts off with identifying the design characteristics, which could be defined in a specification, in a design specification. They are in different forms, but they should always be able to translate them into a property or into a self-contained functional scenario. The most common ones come in the format as cause and effect, so an antecedent and a consequent. An example would be the previous assertion that we had, in which after the rise of the request, we had design property that it should assert the acknowledge signal no more than 3 clock cycles later. Now, another thing to take in consideration when doing the assertion planning would be to partition. For example, we have a very large property here for an assertion, a lot of signal togglings and other stuff in the temporal sequence. This could be made much more readable and much more usable if we would use a sequence construct, put parameters in it, and just transform this large temporal sequence into a very small, readable, and much more usable sequence. Now, we've seen that we have to identify the design characteristics, we have to pull out some design properties, which we could translate directly to in a temporal sequence form. We have to partition them, and then we could start doing the implementation, the actual implementation of the assertions. As with other coding activities, it is recommended that you follow some coding guidelines. This is to ensure efficiency, as well as to avoid some common pitfalls. I've compiled a list here of small coding guidelines. These are not exhaustive, but they're good to remove, let's say, common problems in the assertion development. One would be avoid duplicating design logic in assertions. So it should be recommended that the developer of the assertion should not be the designer. That would be a first step, should not be a designer of the block, as to not contaminate the checking logic exactly with the design logic. This could be also avoided if the reviews done over the design of the assertions with the designer and the verification officer. Another coding guideline would be avoiding infinite assertions. So you could have assertions that don't have an upper range when you have delays in the assertion. Take, for example, we had this one. We have request and no later than 3 clock cycles, we should have the acknowledge. But what if 3 would be missing and you could just put an infinite upper range? So you could just say that after a request, the designer waits for an acknowledge, but it doesn't specify when. Well, this is kind of dangerous, because if the simulation lasts less than until the acknowledge is asserted, the assertion will not be considered as failed, it will be considered as passed. Another basic coding guideline would be to mind the reset. This would mean to always plan that the assertion should work or in the reset or outside the reset phase. So it matters because you could have designs that would work differently. when in the reset phase or outside the reset phase. And another one would be minding the sampling clock, which I know it sounds trivial, but you could just have a different sampling clock for the assertions that could give out some false alarms, and you would invest some wasted debug time. To continue, another coding guideline would be to always check for the unknown condition on the signals. For example, checking only for the value 0 for, let's say, a signal could be issue a false alarm because X's in simulator sometimes are decoded as zeros. So you would like to do an explicit check for X's. You have built-in functions in SystemVerilog for this. The next two coding guidelines refer to having assertion labels that are explicit, which helps with debugging. This can be paired with having detailed assertion messages. Let's say in the fail block, if an assertion fails, you should have as much details as possible. You should not be cheap on this, let's say. And the last coding guideline is related to assertion encapsulation. The SystemVerilog standard offers you the possibility to have the assertions in a separate module or separate file as apart from the design logic. This helps you have them separate, not contaminate the design logic with the assertion logic, as well as you could make a lot of shifts and a lot of reuse by just binding the assertion module to any design that you want to check. Apart from the coding guidelines, we've also outlined some best practices that could help you make the development of the assertions much smoother. One best practice would be to always leave the SystemVerilog assertions with the designers. This can point out design specification misinterpretations, like you could forget about some modes or some aspects of the design when developing the assertions and not check everything. Another one would be using strong in assertions that may never complete. We've previously discussed that in a coding guideline that you should avoid doing infinite assertions with no upper range when you have delays. But let's say we are forced to do that or we have to do that, at least we have a safety net. You could use the strong construct of the SystemVerilog language. What this does is that in this case, let's say we have the request and the acknowledge. If the acknowledge will not be asserted until the simulation ends, this assertion will be considered failed, so we don't get a false vacuous pass. And another best practice would be to make sure that when you develop the assertions, you have thought about all the scenarios. It might not hold under some different modes, like you have a setup mode for the design and you would not like to check it then, or it should be disabled under reset. You have a built-in construct disable if that you could use from the SystemVerilog standard. Another best practice would be to avoid having assertions that could contradict each other. So for example, we have here, let's say, two CPUs. They have different behaviors. One, if it receives a write instruction, issues an error. The other one would never issue an error. If you would put this in two separate files, and let's say we haven't minded the type of the idea of the CPU, and we reuse the assertions, we could end up that one passes, one fails in different simulations. So what we would like, you could just insert IDs in this example, let's say, in which you know that CPU 0 behaves in one way and CPU 1 behaves in another way. So it's a very simple, let's say, best practice, but it could be good to think it before you start implementing the assertions. The last of the best practices is not so known behavior of SystemVerilog. The standard splits the time slot, so clock cycles, into different event regions. This is done for scheduling purposes, but this could also provide some issues for the assertion developer. So for example, for concurrent assertions, the important event regions in a time slot would be the preponed region, the observed region, and the reactive region. So in the preponed region, the values of the signals in the expression for the assertion would be evaluated. So the values of acknowledge from the preponed region will be used when evaluating it. The evaluation will happen in the observed region. And in the reactive region, the fail or pass blocks will be executed after the assertion is evaluated. So let's say the assertion fails, we would have a printout here with the value of acknowledge. But if you would not use sampled function, the value of acknowledge would be from the preponed region, would be from change from the preponed region to the observed region. So it could change in the active region or the non-blocking assignment region, and we could have a false debug message. So what sample construct helps you is that it will always take the values from the preponed region. So the sampled values used also in the assertion evaluation. Now that we've seen some best practices, let's actually start building an assertion. So for this, we've chosen an excerpt from the AMIQ protocol specification. It will be a very simple assertion. We have this excerpt that the bus should only remain in the setup phase for 1 clock cycles and always move to the access phase in the next rising edge of the clock. So what this means signal-wise is that we're first in the setup phase and we should have P-select and P-write signals high in the setup phase, and we also have a defined address and write data. And in the access phase, we just have the enable signal and the ready signal asserted, and everything from the setup phase should be kept stable. Now, to build this, we will separate the setup phase and the access phase. This is good to have sequences so you could reuse them. Let's say we will have to build another assertion, and we could just reuse the sequence for the setup phase. As told you in the previous slide, we have the setup phase, which means that you could have the P-select signal, the write signal, and the P-enable and the ready signal low. And the sequence for the access phase means that we have the enable and the ready signal rising, so asserted, and everything from the previous should be stable, so should be kept with the previous clock cycle value. Now that we have the sequences, we could also just write the property much cleaner and much easier to understand. We just have the setup sequence, setup phase sequence, which will be followed the next clock cycle by the access phase signal. The attached assertion would look like this. It will be attached to the property we have above, and if it will not hold, let's say it doesn't go from setup phase to access phase as we expected, it will issue an error message, and in this case we used the UVM error macro. Now, we've built the expression, we've built everything, the property. Do we know it works as intended? We might even have run it against our design, and maybe it passed, but do we know it works for all the scenarios? So we have to verify it. And this is our main focus in the tutorial, making sure the assertion works as expected. So let's say in ideal world, the verification environment for the assertion should be, in the first place, adaptable, meaning that it should be easy to update it, enhance it, or disable it, in case, let's say, the assertion changes, and that could happen following a late stage specification change. It should be self-contained, meaning it should not interfere with the design logic, it should be separate, so it never affects the design. And it should be predictable, meaning that using the same set of inputs, we should get the same set of expected results. So this is the ideal approach. In reality, the verification environment, if you try to do it for an assertion, will imply tedious work. You end up with something which is non-reusable, and you have to reiterate the debug cycle over and over again for each assertion package. So feeling the need for a more standardized approach, one that could help us ramp up much faster the assertion verification environment, and also hit all these points, plus making the stimuli and the checking much easier, we've developed SVAUnit. So what SVAUnit is, it combines the unit testing paradigm of the software world with the powerful feature of SystemVerilog assertions from the SystemVerilog language. So it is a structured framework that allows you to verify the assertions in an isolated manner. It comes in the form of a UVM compliant package written in SystemVerilog. It provides you with a base class to develop unit tests and test suites to make sure the assertion works as expected. And all of this functionality is also easily supervised and controlled using a built-in API. Now, before we dive in and see how we can use the SVAUnit framework to develop a verification environment for our assertion, let's see how the building blocks of the package look like. First up, the SVAUnit test bench. This is the foundation. Here we will have an instance of the interface that contains the SVAs. You could have, let's say you could just reuse your interface that you already have. You have it defined, you have your assertions defined, and now you want to verify them, so you can just reuse that, instantiate it in the test bench. It also enables the entire framework logic in the test bench and starts the tests. The tests can also stay inside the test bench. They actually contain the stimuli and the checking of the assertion under test. You could put them inside the test bench, but you could also have, let's say you want to do simple unit tests, but several of them, and you could group them inside the test suite. So the test suite is a run container for both unit tests and tests, other test suite. So you could build different verification environment topologies as you need. Of course, you could just put the unit test directly in the test bench if you want to do a quick run, and then plan to make test suites or other topologies. And of course, we have some valuable reports that can be accessed from both unit test level and test suite level. I will talk about them shortly on what information they contain. Now that we've seen the infrastructure, let's see how we could use it to verify the assertion that we've seen previously. So I will use the same example from the APB protocol specification, and we have the assertion that checks that from the setup phase to the access phase we go correctly. So the first step would be building the interface. In our case, we didn't have it available, so we have to build it. We have the interface, it contains the signal definitions, and for brevity and to make the code much easier to read, I've split the rest, the property definitions, the sequence definitions, as well as the assertion definitions on separate slides. So I will explain them shortly on. But for the first, here we have all the signals defined. It is good practice to have configurable widths, so that could also be reflected in the assertions. An address width and the data bus width are present there. Now going into the sequence definitions, they're the ones that I presented earlier on. So we have the setup phase sequence and the access phase sequence. We will then use them to build up the property definition and the assertion definition, as we've seen previously. Now that we have the interface, we have the properties and the assertions inside it, then we can move on to the next step on developing our environment, would be to set up the test bench. So the test bench is a SystemVerilog module. In our case, it's called top. And here, everything is enabled from the SVAUnit framework. This is done with the simple instantiation of the SVAUnit utils macro. This should be familiar with the UVM users. It resembles the UVM macros. The next thing it contains is the interface that we've previously defined. It will give us access to the signals to do the stimuli and also to the assertions to do the checking. So we will propagate it using the UVM config database. And it also contains the run test, which starts all the test sequences and test suites. So we start the tests, and now we want to see how actually the unit test looks like. This is the unit test class is, let's say, the workhorse of the framework. It is derived from the UVM test class, so you have all those UVM-based test features. To define it, it is very simple. It should contain a handle to the interface, which is populated from the UVM config database. We've propagated from the test bench earlier on. As an example here, you could have a disable test method. This one disables the test to not be run automatically, since if you do not do this, you could have all the tests that are added in the SVAUnit framework are assumed to be run. So you add this and you will only enable it if you want to. And we have the test task. Here you actually will do the implementation of the signals, of the checking, of the stimuli. It could be done here in the test task, or we could use sequences. Now we will also add the sequence support. This enables reuse, and you could just have the same stimuli done in several unit tests. Let's say you have something similar and you would like to do similar unit tests. Let's see how the actual stimuli and checking looks like. I've split them into separate code blocks and I will explain each of them. The first step would be to only enable the APB SVA that we want to check. In our example, in our case, it is the example assertion that I showed earlier on. This is not a rule, it is a recommended practice, so you'll avoid false alarms because you will run stimuli on the interface, and if you have several assertions in that package, others might fire, so you would like to disable everything and just enable the one you want to verify. You have to initialize the interface signals. This I will show later on why we need to do this. We have the setup phase where we generate the stimuli and also drive them. We will then drive the stimuli for the access phase and then in the end do the checks to see that the assertion that we want to test has behaved as we wanted. So enabling the SVA is done simply with the built-in API. So we have a wrapper class which is called VPIW, so VPI wrapper. And here we can access all the built-in APIs to control the assertions, check the assertions, provide the reports, as you will see later on. So what we will do first is to disable the assertions and enable our APB phases assertion. Then we have a task to initialize the signals. This is also not a rule, but it is a recommended practice because if we have multiple unit tests, they will be run sequentially, and you could have false signal values propagation from one test to another, which could just lead to false alarms and you have to do extra debug. So it is as a careful step, let's say, to run from a clean state when we do our unit tests. Next, we have, let's say, a simplified example for generating the setup phase stimuli. So for brevity, I've removed the actual generation and only left the constraints here because these are important. So for this simple unit test, in the setup phase, we have two cases when we want to generate valid setup phase stimuli. So we want to see the assertion, let's say, pass the setup phase, or invalid stimuli. This is done simply with a switch. It's nothing complicated here. So we just had fixed values that we need to make a valid setup phase and an invalid setup phase based on what we give as an argument to the task. We've put this similarly for the access phase. So it's a similar approach, simple one. A valid case and an invalid case. Since it is, you could include this in a UVM environment, you could just use constrained random, so you could have valid, invalid, and different other scenarios generated. Now we have the SVA state checking. We've generated the setup phase, the access phase, and then we want to have the checking. This is done using the built-in API from the framework. What we have here is a pair of nested ifs. So if we have valid phase stimuli and access phase stimuli, we will just check that the SVA should succeed. So we use the fail if SVA not succeeded API. What this does is it will check that the SVA state when we run this API should be passed. Otherwise it will issue an error. We could insert as many debug information as you want in the messaging. We just said that the assertion should have succeeded. If we have setup phase and access, valid setup phase stimuli, but invalid access phase stimuli, we check that the SVA should not succeed. And in this case, we use the pair API, which is called fail if SVA succeeded. So it will stop the simulation if the SVA succeeded at this point. If we don't drive neither setup phase stimuli nor access phase stimuli, which are valid, the assertion should not be triggered since it doesn't see the setup phase stimuli. So we expect that the SVA didn't start. This is the last branch you can see here down. So we use the stimuli pass if SVA not started, otherwise it will issue the error presented as an argument. Now we've built the test here, so we have even the checking, the setup, the stimuli, but what if we wanted to check more, say, scenarios for this assertion? We could just build several other iterations of unit tests. The goal here would be to do unit testing is to have simple unit tests, so less prone to errors and much simpler to understand. And we built a regression suite Now, to make a test suite of our simple unit test, it is very simple. You just have to instantiate all your unit tests, so what you've built up to now. You have to create them. This is using simple UVM factory. And then just using the add test macro, you could add the unit test to our test suite. And you're done, and you have a working test suite that when it will start, it will run everything sequentially and provide reports for it. Now, I've talked about the API, but I could show you more. We've split the API into 3 categories. We have control API, a check API, and report API. So the control API contains functions that could help you disable or enable the assertions. You have disable all assertions, that you just disable the assertions in the framework. For example, what we used previously in the previous slides. But you can have finer granular control, like enabling one assertion using the enable assertion API, or all of them. Now, the workhorse, so the checking API, the ones that verify the state is what of the SVA is what we expect, are these ones. I've only listed a few examples from each category, but there are many more which are documented. One, we have fail if SVA does not exist, which needs the SVA name, the one that we want to check, and you also provide the error message. And as for all other APIs, you can provide as many details as you want in the error message, and this is a recommended practice. We also have passive SVA not succeeded. Here, we used this in the previous slides. This API will let the simulation continue if the SVA state is failed, as we expected, or it will finish the simulation. If you want to do some custom error checking, you could just use the pass or fail if check API. Now, we also have an extensive side of APIs for report. So these ones print out a lot of information of our assertion checking. For example, print status will show us which tests or which unit tests or test suites from our verification environment have passed and which have failed. Print API can be used to show which assertions we have active in our environment, which have been exercised, and what checks we have exercised on them. Or you could just use the print report, which print out all these other reports and shows much more details. Now that we've seen also the API, we could just make a quick recap of the entire flow of developing the environment using our framework. You just have to have the SVA unit test bench set up. We could do it as I've shown you previously. You could use a code template that is provided in our library, or you could just upgrade your own top module by instantiating the SVA unit utils macro. The only requirement is that your top module should have access to the interface with the SVAs that you want to test. The next step is to develop the unit tests, or several of them, which will be done in the test task, but as of now, you could just have sequences and have everything defined in sequences and just start the sequence in the test task. The next step is optional if you would like to develop a test suite, so group the unit tests. You've seen in the previous slide, you just have to instantiate them, register them, and everything is done. You can run it. And the only thing remaining now is to simulate and scan the reports and see the information provided. So talking about reports, one of them, the most basic one, would be the error report. It is basic, but it is very important, since this actually shows you when you're finding issues in your assertion. It resembles a UVM error message for those using UVM. It provides the name of the SVA unit check that has failed. In our case, is fail if the SVA has succeeded. So it seems we've expected the SVA to fail up to this point, but it didn't, it passed, so something is wrong. We provide the path to the unit test that discovered this issue, so the one that contains this check, the name of the SVA which didn't behave as expected, and the custom error message, in our case, a very simple one. You could just insert as many debug information as you want. Another report would be a hierarchy report. So this one shows you the topology that you have in your assertion verification environment. as I said, you could build it as you want. So you could have, in this example, you have a main test suite that contains two tests, protocol test 1 and test 2. But it also contains another test suite which goes through a lot of signals and checks them for unknown, for X's, and for undefined, for Z's. You also have a report for what test scenarios you have exercised. So for example, you can see what unit tests have passed, which have failed. The framework automatically flags the tests that have failed with an asterisk, as you can see here. It provides the test counts, how many have been run. We have this similar for the SystemVerilog assertions that have been exercised and the checks that have been exercised on them. So for example, here we have 2 assertions, 2 SVAs, and for each we have exercised 13 checks. Everything passed in this case, but if something would have failed, we provide how many passed, how many failed for each assertion. So these are the APIs provided, the reports that come out of the APIs built in the SVAUnit framework. So to do a quick recap, you just have to set up your own test bench infrastructure, just reuse your top module if you want. You need an interface containing the SVAs, but that is assumed. And then you just can start using the framework and build up the unit tests, since you have all the stimuli and the checking APIs available. Now, as with other coding activities, we've seen some patterns, and mostly for debug purposes, and then for the SVAUnit framework, and then we wanted to see the performance and how much effort is involved in doing a unit test. We've selected some common and temporal expressions and started doing unit tests for them. So this will be what you will see in this chapter, the test patterns chapter. So first one would be a very simple implication test. So we have a simple temporal expression which says that if A and B are asserted, then we should expect C to be asserted 1 clock cycle later. So what we do here, we have a simple randomize phase in the unit test. I didn't show, it's a very simple one. It just calls the UVM randomize in the background. It randomizes the stimuli for A, B, and C signals that we have in our temporal expression. We drive them here. We drive the C signals in the next clock cycles, and then we can have the state of the SVA available, and we can just implement the checks. You could see the pattern starts to appear. You could just have this kind of test for what we used for the access and setup phase example, since it involves also implication. So in this case, we have a similar state checking. If A and B were 1, then we expect C to be 1. So we go here on this branch, and if C isn't asserted, then the assertion will fail. So we check that this happens or not. Otherwise, if also C is asserted, everything should be okay and the SVA should pass. So we check that. Or if not, this condition A and B didn't happen at the same time, the assertion should not trigger, so we should check that it hasn't started. So it's very simple to do a unit test that can be used as the safety net. So you have your assertion, you just do a small change on it, you run the unit test. This is, let's say, the test pattern for the simple implication. Now, we can have something more complicated. Let's say this multi-thread antecedent and consequent. What this means is that you can have multiple threads, so multiple possibilities. You can have B asserted either 1 clock cycle later or up to 4 clock cycle later after A, and then we expect C to be asserted 1 or up to 3 clock cycle later. So what we have here is to do a randomization. We chose to do a randomization of the delays, these 2 delays, and we have them in this case for the valid scenario. We wait the specified the randomized delay, we assert B, and since in this case we expect that the assertion should have started, since we have a valid scenario up to this point, but it shouldn't have been finished because C hasn't arrived. So we have this API to check that the assertion is in motion, it started, it's triggered, but it hasn't finished. Then we will assert C after randomized delay and just check that the assertion succeeded. So because everything what we've driven in this simple unit test is to have a valid scenario. So the assertion in the end should pass. The invalid scenario, we've built it in a separate unit test. It felt like the much simpler solution in this case. As I said, we first started doing these test patterns for debug purposes to see that the entire framework works correctly and how much effort it involves. And this one took, let's say, 20 minutes maximum to build along with this one. So it's much easier to make them in separate unit tests. So here we just have we randomize the delays to be invalid. So we expect that the SVA shouldn't have succeeded up to this point because B was asserted not in between 1 and 4 clock cycles, but different than what we needed. So the assertion should have failed up to this point, but we still go on with the test and see that if C asserts, the assertion should not trigger and it should still be in the fail state up to this point. Another common test pattern we've seen is the consecutive repetition pattern. So meaning that you could have B signal be asserted from 1 or 2 clock cycles, several clock cycles after the A signal, then followed by the C signal. So you could have A, B, B followed by C, or just have one B in between. What we do here is just randomize the number of repetitions for the B assertions, for the B signal assertions, the values for the signals. We drive them here. We weight the number of repetitions that we've randomized. And then, in the end, based on what stimuli we have provided, we can just implement the checks we expect, so to see that the assertion worked correctly. And in our case, we have the SVA should have started but not finished up to this point if you would have had a valid number of assertions and that the A signal has been asserted. So we have A followed by B, and up to this point we should have the assertion started and waiting for the C signal. Going on to the next slide to continue, we also drive the C signal, and again, based on all the stimuli that we've provided up to now, we can start taking decisions. So again, we have a small decision tree here, that if the SVA should succeed, if all the conditions are correct, so let's say the number of B assertion is the one that we've expected, we have the stimuli for C is correct, the stimuli for A is correct, we expect this whole temporal expression to work as expected. So the attached assertion should pass, otherwise we check that it should have failed here. So it has been simpler to just think of the scenario, implement it, and it took just a couple of minutes to do a simple scenario. And this can do a lot more for you, because if you have small unit tests, but hundreds of them, or let's say several groups of them, if you do any change to the assertion, you just run the safety net and see that you didn't change the functional scope, you just made some minor changes to the assertion. Another temporal expression pattern that we did is repetition with range 0. So meaning that it's similar to the previous example with consecutive repetition, but you could have the B signal not just showing up, not be asserted. So you could have A followed by C, or you could have also the B signal in between. And as you can see, the code is exactly as what we had previously. We just removed one item from the condition, and then you can use the unit test for this test, for this temporal expression. So the pattern starts to appear, you just have to remove very small stuff, and it starts to work for another temporal sequence. The same here for the continuation when we check for the last stage of the assertion. And the final one that we've chosen would be the sequence disjunction. That means that here, that after A is asserted, we can have either B followed by C or D followed by E, so in parallel. And what we've done here is randomized all the stimuli, And we've used built-in SystemVerilog constructs like the fork construct, which parallelizes these two checking steps. And what we've done here is, since the temporal expression is in such a manner that you could parameterize or reuse sequences, we've just built in some very small tasks. So, for example, we have a fork, the first one here, where we do the stimuli for A, for B, and for C, and just do the checking phase here. The checking phase is done in the SVA check phase task. It is explained in the following slide. The idea is that we could use the same check phase since we have the same scenario on both threads. So it would mean like this. We have the stimuli for A, stimuli for B and C, stimuli for D and E, each done in its thread. So this is one thread for A, B, and C, and this is another thread for A, D, and E. But the check phase is common, so we just have a decision tree here based on what we've given as argument. So you can check A, B, and C, or you could just check A, D, and E, and we have a decision tree based on their values. So you could just do parameterization, sequence reuse very easily when doing the test patterns as well. Now, as far as tool integration for the framework, there is no requirement. It's simulator independent. It will work on any simulator that supports SystemVerilog and the UVM library. It is available freely as an open source package released by AMIQ. It contains both simulator integration code. It contains the API that accesses the simulator states of the assertions, an assertion package with complete examples on how it is built for the Andra APB, much more complex than I've shown in this tutorial. Other code templates and examples, so you could ramp up your unit tests or the entire framework using some code templates, and also the entire documentation for the API. Everything is, you can take it out from GitHub and it's available. We also have some examples that can be run out of the box. So you just download it, set, and you can just run everything out of the box. To recap, the intention for SVAUnit is to provide a safety net for your assertions. So in case of eventual code refactoring, you can always just rerun a set of unit tests and make sure that nothing has changed functionally in your assertions. It can also be used as a form of self-checking documentation, since now if you would, let's say, ship out a verification component, besides the assertion package, you could just have also the verification package for them. Minor, small, but it can also just show, explain to the other users how the assertions work, since you have also developed a verification environment for them. What we've seen from other users is that it has a quick learning curve, and using the built-in API, which is very easy to use, we hope that it will speed up the verification closure and also increase your quality, since you will have much more confidence that the checking of your verification component or your package works better.
My name is Rodrigo Calderón from Intel. My colleague and I, Israel, work in Mexico, in Guadalajara. So here we are for the first time and presenting this topic that certainly we like it and it is very useful. So at the beginning, we are putting together all this material. We really want to have one picture that depicts everything at once and the correct way. Sadly, we didn't find. Instead, we find something that is the opposite when trying to specify hardware IP features. So the main thing that we want to avoid using formal language, it is the unwanted features or ambiguous features. Like in the comic we have here, so the fail-safe jamming mechanism is one of the most ingenious features of this engine. Sometimes we might find this out of the hardware IPs, that undocumented features, right? So the objective of this presentation is go deeper into the understanding of how to build assertions and echoing the questions that raised before. So how do I understand better how to write formal assertions using SystemVerilog? And it comes down to the specifying objects with properties using formal language. If we understand that, we are just in the other side. And again, using the formal specification for assertion, we can use it for coverage. We can gain comparisons against other methods, for example, per scripting and normal block procedures, like the old way to do assertion. We have those comparisons here to see really the gain to migrate and use this tool more heavily into the IP hardware verification. And again, it is completely different way of thinking, like specifying the features encapsulated into objects and properties. And we can even group all these properties to build more complex scenarios. So the idea is that divide and conquer. But if we link together several sequences, we can define objects and we can define more complex scenarios. So that if we check and define the sequences simple, we can get great benefit out of it. And so having the application in our silicon simulations with assertions, coverage, and assumes out of the design, with the statistics, of course, at the end of each simulation. Our agenda, it is quite lengthy, but we will try to make it soft for everyone. So we will try to give you a very nice introduction why we need all this, all the core components that help us to define the formal language and use it properly and as intended. Also, we will see how to define sequences from the very simple ones to complex ones using some USB examples. We will go through how to write properties, and also we will go through the assertion language, which is not just writing assertions, but having assumes and having covers out of the same specifications that we already wrote in properties and sequences. We will have also comparative results against per scripting and procedural blocks. So the specification. Why do we need all this? Formal language are used to describe design properties unambiguously and precisely. If we leave this room, please keep this in mind, okay? Because even if we think that when we write our specifications for hardware, and if we think that we are not being ambiguous, think twice, 3 times, or even more, right? Because really what we wanted to say using formal specification is more like a mathematical language, having less ambiguity with it and get the benefit being precise. Usually properties are written as part of high-level design specifications in a text document, but writing a specification in natural language is ambiguous, as I said before. And let's look at the following example. Each request should be granted in 4 clock cycles. I repeat it again. Each request should be granted in 4 clock cycles. Does anybody see anything wrong with this? There you go. Okay? So we think that we write it right, but these questions arises. And what type of questions? Do we count 4 cycles starting from the cycle when the request was issued, or from the next cycle? It doesn't say that. Do we require that the grant is issued during the first 4 clock cycles, or exactly at the 4 clock cycle? It doesn't say anything about that too. Might 2 requests be served by the same grant, or should they be served by 2 separate grants? Who knows? So really, if we go to the language and the formal specification and we write it, is what we meant. Everything that is written is what we meant. So let's go and read this assertion, which is encapsulated in a property. We have a posage of our clock, checking for every clock. So once the request is true, immediately after 4 clock cycles, we have a grant. That's what is written, and that's what we meant. No more, not less. That. Going to the question. Okay? This specification defines a clocked or concurrent assertion, and it reads, when the request is issued, it should be followed by a grant in the 4 clock cycle measured from the clock when the request was issued. So we have 2 parts mostly in all the properties. Something that we're expecting to be the beginning of our sequence, which is the antecedent. And once this statement is true, then the following statement should be true as well, and all the time. Just read the last part. When the specifications are formally defined, there is no misplace for misunderstanding. Because we try to write, I should correct, we don't try, we do it, and we write it in a more mathematical way so that there is less misunderstanding from our specification. Okay, going to the basics and how to build our knowledge in formal specifications, we need several components to get that knowledge. The first one, it is the language. We have to pick up a language so that we have the tools, the right components to start building the sequences, and then the sequences encapsulated into properties, and then the properties take some action, right? So the first component is the language. Second, as I said, we encapsulate this into properties, the behavior into properties, and the properties have abstract descriptions. Again, mathematical thinking. And with all of that, we come to this sentence that it says, abstract descriptions are aimed to specify abstract behavior as it defines what happens and when, without specifying exactly how. And really, I want to spend some time on this concept because it is tricky, to be true. It is tricky because it says that we have to define what and when, but not exactly how. And then if we recall the first example that I showed you, we say exactly 4 clock cycles, right? So what does all this mean? So what it really means is that we have to think in a more abstract way, but with several layers in our knowledge, starting from the Boolean logic, then going to add an ingredient that is time, and then once we have the logic and the time added, we have to go to the implications of those statements. And that is implicitly the how. We will go deeper into this, but I want to make sure everyone is clear on this. Again, abstract descriptions are encapsulated into properties just as part of our language that help us to build sequences in a more useful way. Again, a group of properties might describe a complete model. If we divide all the things that we want to check, it is much simpler than if we start with a very complex scenario that might have several branches that we are not seeing as we wrote them. So divide and conquer, remember. And so the application with the formal specification, in our case, is silicon verification to create via formal properties. And again, this is also that I want you keep in mind, is creating evidence that the system exhibits certain behavior, that it is defined or not. Again, it is defined or not. So if it is written, it should be that way because we meant it. Again, this is a very nice slide that I like because it comes down to the way we think. Boolean expressions. So we can recall the Boolean expressions is simple logic, right? We learn it, we know it, but it's a level of abstractions very, very simple, very basic, that it really just is true for one period of time, no more. Then if we go up into our thinking of a more abstract thinking, we have the sequences. So what is really the sequences is logic changing through time. So we are adding elements to our initial thinking, which is Boolean logic, and then we put the values into time in a sequence so that we can check if they are correct or not. And then we need a tool to encapsulate those sequences into properties, but more than that, we need the implications of those sequences. Why? Because once we define what is expected behavior, we need to define the implications of that behavior. And here is the tricky part again, because concurrency in the assertion language is present. So when we are designing hardware, we start thinking in parallelism, concurrent events that are happening. And so the assertions are built in that way so that can take into account concurrency. And these are the scenarios that probably you didn't think ahead when you write the assertions. So this is very important as well. So think again the implications of your sequences when you write them. And of course, if these are defined, we need to take some actions on those descriptions that we wrote. And this is the application already in our simulations to start putting assertions, coverage, of course, and assumes. So the assumes we'll see later that it's a good start for the architect or the designer to say what is expected out of this design to be checked by the validators, for example, without writing any RTL code, but just saying, this is what I really want to be this unit or this design. And so the components that we have for formal specifications is Boolean logic, simple level of abstraction, and temporal logic, which is Boolean logic through time. And here is a note that I want to read for you. Any temporal logic statement is assumed to be in the context of discrete time and might or might not be specified in a discrete event of context. What does it really mean is that you have to have a context for each assertion or each statement that you write. You can write a sequence for a specific module, but this might not be true for a module that is similar to it. So it requires a context for the application. And so we can associate temporal logic to a path in time where a sequence of events occur in a specified order. This is where we start thinking more abstract into our specification. So we have discrete events, Boolean logic happening in time. And then now we have to start thinking how we take these basic elements and like Lego, start this goes first, then this one next, then this one next, and so forth, in an unspecified order. And this can be understood with some structures, like cryptic structures, which are non-deterministic finite state machines. So it is nothing but a model to start abstracting our initial thinking, Boolean logic that is happening through time. Normally, this is what the finite state machines are. We have certain permutations between states, and these are the ones that are valid. And so our specification, we have a starting point, and then we build a model that if we see it that way, like in this figure, we say, okay, this is simple enough, but how we can check the correctness of all of these permutations? One good practice to start understanding this is going into unfold the structure. so that we can define certain paths in the structure to be true. So, for example, we start from state A, and one of the branches can go to C and then C, but then we have a different branch that starts from A, goes to B, and here we have, again, two different branches from the same point. And this is quite useful because if you start thinking in this way, you can unfold the right behavior that you wanted to specify, and probably you will see at some point that it was not what you intended, or it was what you intended. But it is a simple exercise, but it can be really, really useful. And so if we achieve this, we can just start writing the right sequences to define these events, and no mistakes, because are formal. And then we have a very linear path when we unfold the sequences, and are much simpler to think into these simple sequences, discrete events, and no misunderstanding from that. Okay, have understood that part. Let's go to the language constructs, which are the core components to start thinking more with formal specification. So the definition, just very simple, not burdened here. The SystemVerilog language is the one that we pick up for the silicon verification. Nothing to add in that part, and it is covered as part of the standard. And we start with the basics, which are Boolean logic connectors and or non-temporal implications, which again, we start our thinking into define an event or a signal that must be true, and then immediately after, the same time, another event or signal must be true as well, without time. This is very important. Look at the symbol, just 5, figure 9. It is very, very common in hardware design that ambiguity, it is required. So what we meant on this is that certain behavior in hardware might have delays of events. So let's say that you send a request to an arbiter, and this request, you don't know the workload that the arbiter has, so it can span a certain window of time, but just during this window of time, if the grant it is not given, so an error should be issued. And this is one of the powerful constructs that the SystemVerilog language provides, that the events might not appear in a very linear way, so can be distributed in a certain way. Okay, so it is very useful, this part. Just a very basic example, USB symbols are distributed in a certain way, like a spacer between symbols, so that we can keep the throughput through time. So in order to keep throughput in a USB link, certain space must be inserted to keep the rate between the links. So this is one of the examples that it is applicable to it. Temporal logic connectors, this is one of the things that we want to understand from the very basic and core components, because we can define window times or certain periods of time, like 1 clock cycles, 2 clock cycles, but we can have also expressions waiting to be true so that the next signal must be asserted or be true, in other words. But also we have a cycle delay constant or a range. Again, we can define window of times to expect certain events to be true. And these are very, very important to understand. Temporal logic implication, if we recall the last slide, this one, it is just different from the hyphen and the equal sign. So this one implies 1 clock cycle of delay. So the expression 1 is true, 1 clock cycle after, the expression 2 is true. Nothing to be added, just that. Consecutive repetition. Again, this is very, very powerful because many times we have signals that will be repeated during very long window of time. Again, we can go back to the example of USB training where symbols are transmitted during certain periods of time, and there are plenty of them, and we want to count them. So a very useful way to count them is to count the repetitions of the symbol. But sometimes we want a little bit of ambiguity so that I don't care how these symbols happen, I just need that they happen during this window of time. And then you can specify non-consecutive repetitions of those symbols. Also, there is one useful construct that is called goToRepetition that you can specify a certain number of times of signal to be true X number of times. So at this point, what is the difference between these two? Non-consecutive repetition, you are looking exactly for this number of repetitions and must be non-consecutive. GoToRepetition not necessarily needs to be non-consecutive. Slight difference, but important. Also, we have some constructs that help us to build more complex sequences, like throughout statements, within first match of a sequence, intersect of two sequences, for example. We will go over into details with these ones, okay? So, very quick, sequence declaration. We just have sequence keyword, we have to give a name, and then the sequence variables in between with the end sequence. Sequences, again, encapsulates a temporal preposition to make it reusable for the design. The same goes for property that encapsulates behavior. So we jump into the examples. Everybody wants to hear those. So my colleague Israel will talk about those.
So sequences. With sequences, we can think about a series of ordered events happening one after another. And we have seen that a couple of times in receipt steps for designs, or the loading values in registers, or like in the USB protocol and other protocols, we have to pass certain states and make some handshakes in those states to get our design to a point that we can say we are going to do a transfer. So take, for example, this one. We have AV, AV. All this is a sequence of events that are happening one after another. These sequences are really important, and we can define them in several parts in our SystemVerilog language. We can define them in modules, interfaces, programs, clocking blocks, packages, and in unit scope. For example, we have the last sequence that I showed you, and we are checking for it to happen. It was AV, AV, followed by a C. So in this example, we see that, as Rodrigo has already mentioned, we have a series of Boolean expressions that are looking to be true, and one clock cycle after the other, we are looking for another expression. And we can see that in the simulator. Here we have A, B, and C. We have the values 1, 3, 2, and AV, AV, and C. And when that happens, our sequence is completed, the signal is asserted. So it happened. So how are we making our sequences? As previously mentioned, we are using some Boolean expressions. Let's take a simple example of just one signal, that is E. And E, in all this is a time, and we have many clock events in this time. So if E exists in one of those clock events, then it's true. And if it's true, then we can say that our sequence is completed. To connect multiple Boolean expressions, we are going to use the temporal logic. And the temporal logic is defined with two hashtags. These hashtags help us to define an amount of time or separation of time between all these Boolean expressions. And that time can be defined with a value, a simple 1, 2, 3, or a constant. We can also specify ranges using the square braces, or even we can think about infinite, like we have already seen with the previous presenters, using the $sign. But we have to take care, or just be aware that if we use it too much, the resources of our system are going to be far too much, and the simulation is going to get really, really slow. Here's an example. Let's say that we are looking for R to be true, and on one clock cycle or clock event after that, we are looking for S to be true as well. So we can see in this picture that R is active for 3 clock events, and one clock cycle after the last R time that was true, S come to be true as well. So in the simulator we can see that as well. We have R, and the last time that, for example, this one was true, in this clock event, 2 clock cycles, here S is true. So we are getting this S, or this sequence, sorry, to be asserted in this period of time. We can also have the fusion of Boolean expressions using the 0 and the double hashtag 0. Here R, we are looking for R, and at the same time, we are not waiting any time, we are looking for S to be true as well. And in the picture, that's what we can see. We have R to be true all this time, this Boolean expression to be true, and S. In this event, S exists as well, so our sequence will be activated in this clock event. And we can also add multiple delays. Multiple delays, we can have here a certain amount of time to look for one condition to be true and the other looking for that to be true. The example says R is, this Boolean expression is true, and 2 clock cycles after, we are looking for S, or this other Boolean expression, to be true. The picture shows that, but we can also see it here in our simulation. 2 clock cycles after, as it's shown in this example, we have the assertion of our sequence. So here we can see that it happened as well. So here's an example when it's not happening. We have the request sign up. One after, we look for the grant and the neg of the request. And all of this, does anyone see the problem here? Grant's not there. So that's why we are not seeing the sequence to be completed. We can also play with ranges. We can look for a certain clock events for a certain Boolean expression to be true, and that's what we show here. This Boolean expression and a certain amount of clock events, we are looking for this other one to be true. And here it comes from 3 to 5. M will be 3 and N will be 5. So here is the R. R occurs here, and 1, 2, 3, 4, and 5. Because 4 is in the range that we are looking for, we have here the sequence to be asserted, or it's working. And we can also add the delay at the very beginning of our definition of the sequences, instead of starting with Boolean expressions. We have here, we have a delay at the very beginning, and we are looking for the Boolean expression. So we have the picture here showing us that. Now, we can encapsulate all the sequences and use the repetition, which is also very powerful, to tell us a series of events happening. We have A to after look for B, and this repeats one other and another time. 5 times it repeats. So instead of writing it this way, we can just do it this way, and it's cleaner and easier to understand. We can also do that for the time connectors. So we will be looking for R. For example, let's say that M was 1, 2, 3, R, 1 after, we're looking for S. Or R, 2 after, we're looking for S. Or R, 3 after, looking for S. and the same can be done using the dollar signs. We will have multiple threads doing all this checking. Here is just an example of the repetition, but instead of doing it with 5, we are doing it with 2. So we have these events happening, and here is when the sequence is being asserted. As Rodrigo previously mentioned, we have the go-to repetition. Go-to repetition, they are not forced to be consecutive, and we have it here. We are looking in the example for E to happen 2 times, and after that we can do another checking. But here happens E, and a little time after that happens again. And we have a picture of the simulator or an image of the simulator here, that here happens, and in this case is R, happens here, and a non-consecutive time or a certain amount of time it happens again, and when it happens the second time, our sequence is asserted. The non-consecutive repetition, it's pretty similar to a previous one. The difference is that it's just followed by sometime by T, while the other one is next. It's like immediate, more immediate. And we can also specify ranges using the colon here. Here we have another example. Here we're looking for the sequence, and we have these Boolean expressions that are A and C, and we are looking for a loop here. It will go from 2 to 10 times. It will repeat and repeat, not consecutively, and we are expecting that to happen. We just need to be careful with the number of threads, and here we see it. A is happening here in this clock event, and one time after that we are looking for B. B at the second time it happens, and one clock cycle after that, C is true, and our sequence gets asserted here. But since we are using multiple threads, or we are specifying multiple ranges, then it can happen in the third time, fourth, fifth, and so on. Just to when this condition of one after that C appears, then we have these other events or the assertion of that sequence. Okay, now that we have defined all the sequences, we can just use the binary operators to connect all of them. For example, we have here the AND. The AND, we have 2 sequences, let's say sequence A and sequence B. And with those sequences, we are just looking, or with each clock event, we are seeing that both of them, their checking starts at the same time, at the clock cycle, but they are not necessarily going to finish at the same time. So let's say that A finishes before B, but since this AND is connecting these 2 sequences and they are not forced to end at the same time, then once B is finished, then our whole sequence made of these 2 sequences is going to be asserted. So we can say that they start at the same time, and the operand that finishes has to wait for the other one that hasn't finished yet for the sequence or the whole sequence to be true. And we have also the example here. Here, this T1 and T2, which is this part, is happening long after the other one. But we have to wait for this other sequence to be true to get the completion of both. So when this second sequence is finished, then we get those 2 to be asserted. Then we have the intersect. It's pretty similar to the previous one, to the end. The condition is that they'll finish at the same time. They have to start and they have to finish at the same time. So we have that. We have both sequences starting at the same time. The operations will continue, and if they finish at the same time, then we are going to say that our sequence using the intersect is work. So that will be the only difference with the AND. And here we have another example using ranges. That this sequence has to intersect. So this sequence, the first one, repeats, or it's true for several times, but only when it is true, the second part as well, we are going to get both of them to be asserting our sequence composed of these two. The other works exactly as we will think. Or one sequence is true or the other, and when one of those things happen, then we are going to have the completion or the assertion of our sequence. And here we have the example. We can see that in this both of them are true, but in the other events just one or the other is true, but it gets asserted. Throughout is another case, and it just needs a expression or distribution to be true while this sequence is working. So we have here the condition is true while the sequence starts. It's checking at the clock event. The condition is true, and the sequence finished. So then we have our assertion of our sequence with the throughout. The within. The within is a sequence within another sequence. It happens and is encapsulated by another sequence. As we can see here, there's a sequence within another sequence. So this is another tool and another binary operator that we can use. And we have it here. We have this Boolean expression within these conditions. And we see here as well that the condition is within this condition and this other sequence that is happening with this constructor that is fell, the fell dot signal IRD, and one after we are looking for the repetition of a not of IRDY, and well, here it gets the signal or our sequence assert. So we can also use another kind of methods that are defined with each and every sequence that we have. For example, we have here the ended method, just to be more clear and let's make our code easier to maintain. And as well, we can do some manipulation inside our sequences. As we can see here, the X signal, we have the value of the piping. So we can see the benefits of using the sequences as well and manipulating the values within the simulation. And we are going to jump into the USB examples. Some USB examples, well, we have the training in the USB, and let's take, for example, the LFPS is one state of the protocol, and it's looking for ones and zeros to do the handshake between the host and our device. So, for example, we would like to detect the zero of one of the states of the USB protocol. So this one will be the zero. It's a little shorter compared to the one, and we are going to look for this time that the signal is asserted. So we are going to count for the repetition from 1 to 16 or 17 of the signal to be deasserted, and a time after that we are going to look for another time when this signal is asserted. So once that happens, here we can see that our sequence was completed, and that's what is shown here. It's, for example, from 16 to 18 clock events, it repeats. Here we can see the asterisk, and what clock cycle after that we are looking for that signal to be hold true for a certain amount of repetitions. And once that happens, we have the LFPS 0 to be detected, and one of the parts of the USB protocol, or one of the symbols from the handshake, to be true. And now the one. The one is a little bit more, well, its length is greater, and it will be this one or this other ones. And we have it here. It will take the same time being deasserted as the 0, but as mentioned, the time that it will be asserted, it's bigger, and here it's 118 and 189. So here are the values, and we see that the sequence is exactly the same. We have the first part, that's the duration, and we're using the repetition of 16 to 18, and one after that, we are looking for the signal being asserted. And once that happens, then we have the assertion of our sequence. Now, that was just one part of the training. Other part or other state from the training will be the RxEQ state. And in this state, we are sending certain symbols that are 87 symbol, actually, 87, 87, and actually 4 87s. So we can divide this sequence in 4 parts. This will be the first one, and here it's fine. 87, 87, 87, and 87. And our sequence is really simple. We define it as TSIC A part detection. And we are looking just the data and that value to be true. And it's happening here. We can see the arrow here as well. And the second part, it's almost like the other part. We have this value, but change from the previous one from 87 to 0. And we can see as well that here it's granted, so the sequence is detected. And finally, the assertion of the whole sequence, composed of the A part for 1 clock cycle, the B part, and 1 clock cycle after, we are going to find the A's repeated. So that will make our whole USB 3.1 training state sequence. And it's very useful, and you can use it. And as you can see, because of the way it's written, it's easier to maintain. And so now my colleague is going to talk.
Continue with our basics of understanding the formal specification. We go deeper into the details, what is inside the property specification, and basics, the definition. What is a property? A property defines an abstract behavior of the design. The result of a property evaluation is either true or false all the time, okay? And as we see in the previous sequence, the sequence was true, but just we showed that when it was true one specific period of time. But there are many cases that might be not true, but the evaluation always takes place, okay? So property definition is based on prepositional and temporal logic, which deal with simple declarative prepositions or simple declarative prepositions through time respectively. What we have to keep in mind out of this definition is that we used propositional and temporal logic, okay, which will help us to define the implications of the property. That's what we have to keep in mind. The combination of some propositional, temporal logic elements with generate for can lead to first order logic. And this is just going to the basic, what is behind what is going to take into account your simulator, okay? Your simulator is built in such a way that takes into account these rules to know where to check these formalities, just to let you know. And they use the first order logic to perform that operation. So a property can be understood with a combination of temporal propositions, all together happening at the same time or different times, but they must be present so that the simulator can interpret the language and define that is a property. Okay. One of the elements of a property is the predicate that resembles a function that returns either true or false. In here, again, we can just specify a sequence that match or do not match. And if the sequence that is in the predicative do not match, we do not start our property checking of the implication, because the first part, it is not true yet. What first order logic allows us is reasoning about the properties that are shared by many objects through the use of variables. So really is just to get the understanding for the simulator what is going to be checked into our definition. Here is what is, just a picture say more than words, is propositional and temporal logic plus quantifiers is equal to first order logic. So in general, we will have these descriptions of functionality, but then we incorporate the quantifiers. And these quantifiers, whether they are true or not, together they build the foundation of first order logic. And this first order logic is being checked by the simulator. Okay? This is just a little bit of background where it comes from, this language. SVA property can be defined into a module, interface, program, clocking block, a package, and compilation unit scope. One of the things that we have found out through the experience is that the most useful place to define properties are embedded into the interfaces. Interfaces between anything you want to communicate. So one block to another block, one IP to another IP, and this interface can be a standard interface or can be just intermediate interface inside a module as well. That's why it's very useful to be defined into an interface, because if you define properties into interface and then you build assertions or coverage or even assumes out of this interface, and the interface turns out to be a standard interface, you can just reuse the interface from project to project, and it's quite powerful. That's a good practice to be followed. And again, if you define the property declaration, it doesn't do anything the simulator before you place it with an assert statement, a cover statement, or an assume statement. Okay? So it is just the description, and that's it. And there are several kinds of properties, of course. We have the sequence itself, the negation of a property, disjunction, conjunction, if-else statement, implication, and the instantiation of the property, so that we can make reusable the descriptions of the properties as well. Just a very simple example here. We have the definition of this rule with no type. So one of the things that I want to point out is that we can define our properties to be, think of like functions that can receive arguments. And if we define them in such a way, we can reuse them as well, so that we don't have attachments to the types of the variables, but the correct behavior of them, which is quite powerful, and you cannot use it in every language, right? But SystemVerilog. So we can use property type as sequence. So we follow this example. We define the property, and we have defined we need a clocking statement, and we start specifying our checking. In this case, so there is the difference. So we have a sequence, but inside a property. It is not a sequence itself embedded into a sequence block, but it is just a sequence plane inside the property body. So if we define this piece of code, this line of code, and we replace the keywords properties and property and property by sequence and end sequence, we will inherit the properties of the class sequence. Sequence is a class, and we will have the methods embedded for them. But in this case, we are defining a sequence within a property body. And we don't need, by the way, any implication in the property. So just this plain sequence itself. So negation. So again, we can have a property or an expression to be true or not all the time. Even can be a variable, can be just a counter to be true, or a reset to be present, etc., etc. Okay? We can negate. So disjunction again. So the disjunction, our colleague Israel mentioned it before in the examples, but I just want to point out one key element of this is that all the time either property 1 expression or property 2 expression must be true. If any of those are not true, we are going to have an error. Okay? Very important to know. And conjunction. So this is the opposite, right? So we can have this one and this one all the time. This is what we want and must be true. In addition, we can include if-else statements inside the body of a property. And look at the second example here. So we're specifying the property expression can be true within an expression or distribution. This is the powerful of one of the first slides that I showed you before, that sometimes our features or the behavior of the hardware, it is kind of flexible, but within just windows of times. And this is just, you don't imagine how powerful is this one. So it can encapsulate a lot of behavior, and it can save you a lot of code to be written. The implication. So the implication, this is one of the main features of a property, which we always have or tend to have an antecedent, not always, which is a sequence or can be a sequence, but we always can have a consequence if we include the implication symbols. So this can be understood as immediate checking, because sequence expression must be true, and immediately after property expression must be true. And the opposite side, this sequence expression can be true, and one clock cycle after property expression must be true. Just to make clear the difference between those. One of the most common mistakes in writing properties. And again, we just say the instantiation. This example is interesting. First, let's go to the picture and see where the statement is true, starting from that part. So we have this sequence that it is true just on this time. But we look at the graph and see that the stop signal is falling, the T ready is high, the I ready is low, and the data phase is high. And we go to the description of our property where it is supposed to state the data end. So we will see that this data phase, once the data phase is high, something must be true immediately after. What? So all this expression, but we go step by step. First of all, we need I ready to be equal to 0. So if we look at the graph, I ready in the second clock cycle, it is true or not equal to 0. So in this case, we will write an error. So if it is asserted, included in an assertion statement, yes, we will have an error, but if we put it inside a coverage, so it will not be counted, etc., etc. But we have to be very careful with this description, because, as I said, once the first statement is true, the next one, when using implication, must hold true. So if we look at the first term of this second expression, where I ready must be low, so it is not true until this point. So the previous clock cycles, this statement will flag some errors. So just a very quick overview, what is all about assertion language. So assert, just take the action to specify if a certain behavior in our design is correct or not. That's it. That's what it can be inside. And normally we use it for the design under test checking mechanism. So continue with the assert language. We have two types of assertions, immediate assertions and concurrent assertions. And one implies time and the other one does not imply time span. Concurrent assertions imply time span of checking. So just a classification of those. So immediate assertions might not contain temporal expressions and might be inserted anywhere in the procedural code, and are evaluated as statements. And concurrent, it might contain temporal expressions, and this is one of the most important features of the concurrent ones, because they are variables that are going to be sampled. As our colleagues from the first part of our presentation of this tutorial state, you need to be careful on when the signals must be sampled, because you need clocking scope of the checking. Immediate assertions, this is just for your reference, how the syntax of SystemVerilog goes. And again, this is all for your reference, what are the components that can be put inside the assert expressions. So we go to the assertion name. This is how your simulator will identify and classify the assertion checking. We can't have guard expressions like resets, so very good practice to put these ones, and also put meaningful messages for passing and fail times. So we continue with the system task. As we said, we can specify this type of information, and this is just for, again, for your reference, how the old way of writing assertion goes. You see about 10 code lines just to check if a state is equal to request. So it's up to you to write more or not. Concurrent assertions, this is just also for your reference how they are classified, and they describe behavior that spans over time. That's what I said before, and the evaluation model is based clock. You need to specify the clock for your sequence. Let's say, for example, that you define sequences inside module block, and you don't specify clock signal inside your description of the sequence. Does the simulator will flag an error or not? In the case of the module, will not, because a module, if it contains, well, it depends. If it contains a clock domain, the sequence will take as a fact that clock domain to perform the sampling of the signals. Okay? If the module does not contain a clock, it will flag an error because it needs a reference to sample the signals. So it is just to make sure that we take into account the sampling always. Again, just an example on how the labeling of the different parts of the assertion goes. And this is one of the useful slides that we have to take into account the sampling of the signals. And also this is a complementary of the previous presentation, where the actions are taken when including sequences and the sampling of the variables that are included in a sequence. So the sampling is in this region, the evaluation over here, and the actions over here. Just to keep in mind that you are going to be working with sampling of the variables, and you need to take into account that. Classification of the verification statements, what they are, I think I don't need to add more information on this. Everybody knows what an assert statement is, the function on each evaluation ensure that property holds, but the intent is the one that it changed for every one of these blocks. The intent for an assertion is to properly check for design under test register level transfers, and assumes the intent is an assumption for the environment. For example, I intend that the transfer happens in 3 clock cycles, not in 4 clock cycles. And it is very useful for architects and designers to start from scratch a project and start defining the assumptions under the design will work. In coverage, the statement cover, so it is an indication of the evaluation to check if the property was covered or not. So intended for functional coverage. So a little bit more information of the assertion. So for design verification, it checks the property correctness for a given simulation trace. Only for that. So it can be true that the stimuli for a test holds the assertion to pass all the time, but for another stimuli of a certain test will not be true. And you have to play with that. So another example. So going to the assume. So the assume, I think this is a little bit more higher level specification, again, for architects and designers to start from scratch and start saying, okay, I want the design to follow these rules. And not necessarily an assume statement will give errors when they appear, but probably, depending on the simulator, will give you a report whether the assumptions hold or not. And can be useful to evaluate architecture or can be useful to evaluate the functionality of the design. It is treated the same as assertions, but the intent is different, of course. And this is what I said. This is not a requirement from the tools that make a report for us. We have to look for it. And the specification, it goes the same as an assertion. I will go quickly over this. So if we have a set of properties that we write as assumes, with the intent to be assumed, so we can have this set to be labeled as this one. So having the property 1, property 2, and property 3. The coverage, this is also very useful because once you have described all the sequences, all the properties, you can assert those sequences, and either you can decide whether or not they are going to contribute to your functional coverage. So again, if we think about putting sequences and properties inside an interface, you can get a lot of benefits, not just for checking, but also for functional coverage checking. The same syntax goes for cover, just interchange and as an assertion. And last, I hope you have learned something today. We just have compiled some comparative results for assertions, writing assertions versus scripting or procedural blocks that normally goes for assertions inside the RTL. So my colleague Israel will just conclude with this section.
Yeah, well, this will be the last part, and we did the exercise of using Perl scripting with a tracker, how many lines of code we needed to check for the sequences to match, and we saw that just taking into account the sequences, it happened to be 3.5 less effort doing it with SystemVerilog and all these temporal logic tools. And if we consider the assertion and cover characteristic, it was almost 2 times less effort. And doing it with the always and kind of a Verilog style, we found that the effort was from 6 times less as well, just taking into account the sequences, and when taking into account assertion and cover, we saw that it's 3 times less. So it's less effort and easier to read. And here's an example of a tracker. Here we can see that we have the zeros and ones, and the parsing done with Perl scripting result in a 41 lines of code required to process this sequence in a protocol. Also, we did it on, with the example or the exercise with Verilog, and took us 74 lines of code to do the same. So it is less coding effort. Doing it with the SystemVerilog and all the tools that we have shown all of you, it was just 16 lines of code. So it's a good save of effort, and this is one of the advantages, and the maintenance, easier to read and all that stuff, it really pays.